What are spiking neural networks? Executive summary. Spiking neural networks are a highly energy-efficient alternative to traditional artificial neural networks. They mimic the brain by using discrete, all-or-nothing electrical pulses, called spikes for communication. Information is encoded in the timing and frequency of these spikes, known as temporal coding. Unlike ANNS, SNNS only calculate when a spike occurs, leading to dramatic power savings. They require specialized hardware called spiking neural processors, SNPS, such as those developed by companies like Inatera. SNNS are ideal for ultra-low power devices and real-time sensory processing, especially at the network edge. Articles spiking neural networks, SNNS, represent a third generation of artificial neural networks. They are fundamentally different from the artificial neural networks, ANNs, most people know. ANNS, like those used in deep learning, process information continuously. SNNS, however, use discrete events in time, mimicking the biological brain. How biological neurons work. The human brain is the ultimate inspiration for SNNs. Your brain contains billions of neurons. These neurons communicate with short electrical pulses called spikes, or action potentials. A neuron waits until it receives enough electrical input from other neurons. When the input reaches a certain threshold, the neuron fires a spike. This spike is a burst of electrical activity. It then travels down the neuron's axon to connect with other neurons. This all-or-nothing event is the basic unit of communication in your brain. The problem with traditional ANNS. Traditional artificial neural networks use continuous mathematical values. These values represent the activation of a neuron. Information travels as a stream of numbers through the network. This process works very well for tasks like image recognition. However, it requires significant computational power. Every neuron calculates an output for every input. This continuous calculation leads to high energy consumption. ANNS are generally implemented on standard computing hardware. This hardware is not optimized for brain-like computation, introducing spiking neural networks, SNNS. SNNS replace the continuous activation with discrete spikes. A neuron in an SNN only sends an output when its internal voltage reaches a threshold. The output is a single binary event, a spike. The information is not in the magnitude of the signal. Instead, the information is encoded in the timing and frequency of the spikes. This is called temporal coding. Key differences from ANNS. Event-driven SNNS only perform a calculation when a spike arrives. They remain dormant otherwise. ANNS calculate continuously. Temporal dynamics. Time is an intrinsic part of the computation. The precise moment a spike occurs is important. ANNS largely ignore time. They are a spatial model. Energy efficiency. SNNS are significantly more energy efficient. They consume power only when a spike is fired. This efficiency is critical for mobile and edge computing. The Leaky Integrate and Fire, LIF, model. A common model for SNN neurons is the Leaky Integrate and Fire, LIF model. This model describes the neuron's behavior simply. The neuron has a membrane potential, which is like its internal voltage. Input spikes increase this potential. Over time, the potential leaks or slowly decays back to a resting state. When the potential crosses a threshold, the neuron fires a spike. The potential then resets to its base level. This simple yet powerful model captures essential biological dynamics. Training spiking neural networks. Training SNNS is more complex than training ANNS. Standard backpropagation, the technique used for ANNS, relies on continuous differentiable values. Spikes are discrete events. This discreteness makes calculating gradients for backpropagation difficult. Researchers have developed several clever methods to address this challenge. Conversion method. You can train a standard ANN using backpropagation. Then, you convert the trained weights into an SNN. This is a common and effective method. Spike timing dependent plasticity, STDP. This is a biologically inspired learning rule. It governs how the connections, synapses, between neurons are strengthened or weakened. If a presynaptic neuron fires just before a postsynaptic neuron, the connection is strengthened. The timing difference is crucial. This method is unsupervised and extremely power efficient. Surrogate gradients. This method approximates the non-differentiable spike function. This allows researchers to use a modified version of backpropagation. This is currently one of the most effective training techniques, spiking neural processors, SNPS. The true potential of SNNs is realized when they are run on specialized hardware. These are called spiking neural processors, SNPS, or neuromorphic chips. These chips are designed specifically for event-driven temporal computation. They physically model the neuron and synapse structure. This hardware/software co-design dramatically improves speed and energy efficiency. Innatera. Innatera is a company specializing in neuromorphic intelligence. They focus on ultra-low-power SNN solutions. Their technology is used for tasks like sensory processing. This includes things like recognizing sounds or analyzing vibration patterns. Their chips are designed to process complex data in real time. This processing occurs directly at the sensor, or at the edge. IgnisCore RO. IgnisCore is another innovator in the field. They develop robust, high-performance neuromorphic cores. Their IgnisCore RO technology likely refers to an internal research or development core. These cores are often designed for maximum flexibility. They allow researchers to test various SNN architectures and learning rules. Such cores push the boundaries of energy efficiency and computational density. T1EVKRO. The T1EVKRO likely refers to a T1 evaluation kit from a neuromorphic hardware provider. An evaluation kit, EVK, is a development board. It lets engineers and researchers experiment with the chip. The T1 could be the name of a specific processor generation. The RO might indicate a specific version or region. These kits are essential for developing and testing SNN applications. They provide a physical platform for interacting with the specialized hardware. The future of SNN's SNNS promise a future of truly brain-inspired artificial intelligence. They are not intended to replace all traditional ANNs. Instead, they excel in specific application areas, key application areas. Edge AI, SNNs are perfect for devices with limited battery life. Think smartwatches, hearing aids, and remote sensors. Real-time processing. Their event-driven nature allows for ultra-low latency responses. They can be used in autonomous vehicles and robotics. Sensory fusion, SNNS naturally handle time series data, like audio and video streams. They can efficiently combine inputs from multiple sensors. In conclusion, SNNS represent an exciting shift toward biologically plausible AI. Their event-driven nature and focus on temporal coding deliver unmatched energy efficiency. Specialized neuromorphic hardware accelerates this potential. Companies like Innatera and the development of cores like IgnisCore RO are driving the field forward. SNNS will eventually be integrated into devices everywhere. They will usher in a new era of always-on, low-power intelligence.